Hello, we continue the problem where a rock was thrown vertically up, then falling down from the edge of a cliff down to the bottom of the pit. We can see two graphs here. First graph is a graph of coordinate as function of time. Second graph is a graph of velocity as function of time. We clearly see three pieces of movement here, from B to A up, from A to B down, and from B to C down to the bottom of the pit. Also, we can consider the fourth movement here is the whole from B through A and B to C. So here we see that each of those pieces which we can separate, which we can take out, each of those pieces has its own delta S, delta T, each has own initial velocity and final velocity for that specific piece. Why is it important? Because we can take out a specific piece and solve problems easier just considering that specific piece. For example, let's consider piece falling down from B to C. Acceleration pointing down. Initial velocity at point B pointing down. Final velocity pointing down. Sorry, everything is pointing down. So that means it's easier to choose y-axis direction down, not up. And everything will be positive then. Acceleration due to gravity will be positive. Initial velocity at point B pointing down will be positive. Final velocity as calculated will be positive. So what this shows is you can take out a specific portion, like piece of the whole movement, and consider its own delta S, delta T, initial velocity, final velocity, and so on. It will be easier to solve problems this way. So in our graphs, we see all the parameters that we calculated. Delta S, all of them, delta T. Also we can see that initial velocity at the very beginning of movement is a tangent of angle of inclination of the tangent line at the point B at the beginning of movement. This angle alpha is less than 90 degrees, so its tangent is positive. But at the very end, at the point C, the same approach. Velocity is a tangent of angle of inclination and of point C of this graph, and we can see that this angle is more than 90 degrees and its velocity therefore as tangent of angle of more than 90 degrees will be negative. On this graph, this is velocity as function of time, straight line, linear function. We can see that velocity at point A here is 0. Velocity at point B is negative. At point C is negative. And the initial velocity is positive. In here, tangent of angle of inclination of the graph to the horizontal axis is actually our acceleration. Our acceleration due to gravity is negative. Angle is more than 90 degrees, so it's everything fits. This graph is a standard quadratic function graph. We have our equation of the quadratic function, and so we can see here is comparing to our formulas, we don't have delta here, not delta T. That's because usually in physics T0 equals 0, so delta T becomes just T for simplicity. For delta Y, if we take out y0 put to this side, we'll get yt minus y0, it will be delta y. Now for this function, it's a linear function, standard equation. We have slope, we have constant coefficient. So our slope is acceleration. Our constant coefficient is initial velocity. If we take out v0 put to this side, we'll get delta v equals vt minus v0. And this is, again, this is just a standard linear function. We already considered this. And the final important thing that we wanted to discuss is sometimes people get confused. They think that if acceleration is negative, then body is slowing down. It's not the case. Body is slowing down or decelerates only in case when velocity and acceleration, they have opposite directions. So if velocity and acceleration have opposite directions, then body decelerates. But if velocity and acceleration have the same direction, then body accelerates, it's speeding up. For example, if velocity positive, acceleration positive, acceleration. Velocity negative, acceleration negative, it's still accelerate, like speeding up, acceleration. But if velocity positive, acceleration negative, or velocity negative, acceleration positive, then body will slow down.